Hello everyone. In this video we're going to study examples from chapter 8, which is all about inferences based on one sample. My name is Fred Rispoli and I'm coming to you from Stony Brook University. So to provide an overview for this, we're going to discuss examples involving inferences for means with population standard deviation known. We'll look at these in examples 1 and 2, and then also inferences for means when sigma is unknown. We'll examine this in examples 3 and 4. Again, the examples are based on frequently asked questions by students and frequent errors on test results. Let's start out with an overview that I've put together in terms of a tree for hypothesis tests, or if you want, you could think of this in terms of chapters 8 and 9. In chapter 8, it's all about one sample tests, so the left side of this tree. Chapter 9 is all about two sample tests. Okay. In this video, we're going to focus on tests for means and some other related inferences like determining sample size and determining the probabilities of various errors. So we're going to cover these two cases that you see down here in this video, and in a second video we'll take a look at inferences involving proportions and variances. So as you could see over here, in the first group we're going to look at cases that have fairly large samples. By large I mean n greater than or equal to 30. We're going to look at what you may call the z-tests, and of course all of these sort of assume normal distributions. In the second case of this video, we'll look at some smaller samples when the population standard deviation is unknown. So these will involve a test called the t-test and the t-distribution. Okay, so here are some of the facts for the inferences for the mean when sigma is known. We get a confidence interval. We'd write it like this, a 100 times 1 minus alpha % confidence interval. So for example, if alpha is 0.05, this term becomes 0.95, and we get a 95% confidence interval for mu. Okay, so this is assuming a normal distribution, and sigma is known. So we get this formula x bar minus z alpha over 2 times sigma over the square root of n. So notice this is really plus or minus term. X bar is the sample mean. Z alpha over 2 we look up in a normal distribution table. N is the sample size. If we'd like to know the sample size of a confidence interval to obtain a maximum error of E, then we get a formula here. N is equal to Z alpha over 2 times sigma divided by E, this whole quantity squared. Okay, so this may remind you a little bit of what we see over here. Basically, we're setting this, sometimes called the error term, equal to E, and then we solve it for n. That's how we come up with this formula. When testing a hypothesis, we're going to use this test statistic called Z. Z is x bar, or sample mean, minus the hypothesized mean, divided by sigma over the square root of n. And we find our critical values from the normal distribution. Okay, we will also go through what's known as the 5 steps for testing hypotheses. The first step is to set up the null and the alternative. If it's given, try to identify which of these is the claim. Often the claim is the alternative, but not always. In step 2, we determine alpha, usually given in textbook problems, but if you're running a research project, that would take some thought. Step 3, choose the test statistic formula and the critical region. So generally you have to think if you're going to use Z versus T or perhaps something else, and find something we'll call the critical regions and critical values. Step 4 is to substitute the given values into the test statistic formula and make a decision whether to reject or fail to reject the null hypothesis. So your statistical decision is always in terms of the null hypothesis, and usually given in terms of we either reject or fail to reject the null. Step 5 would be to calculate a certain probability we'll call the p-value, confirm the decision obtained from step 4, and try to give a practical conclusion in the context of the original question or problem. So we'll be following this format throughout this video, and also this should be done on homeworks and tests. All right, so example 1, suppose the shelf life of a certain sunscreen is known to have a normal distribution. A sample of size 120 tubes gives a sample mean of X bar equals 36.1, and let's say it's known that the population standard deviation is 3.7. So we're asked to construct a 95% confidence interval for the population mean shelf life. And suppose the researcher believed that before the experiment, the population standard deviation was 4, what would the required sample size be to estimate the population mean to be within 0.5 months? So there's our error E, and with 99% confidence. Okay, so let's run through how we could solve these. So first thing to note is that the population standard deviation is known. Okay, so we want to find a confidence interval for a mean. So that brings us to this formula that we talked about a couple minutes ago. We know the sample mean. Here's the population standard deviation. So we substitute in 36.1 for X bar. Okay. We want a 95% confidence interval. So that tells me that alpha is 0.05, and we need to divide alpha by 2. So we have this z alpha over 2 is z.025. We need to look this table up in a normal distribution table. So we want the value that leaves, let's say, 0.975 to the left. That value is 1.96. We'll see that on a table. As you can see over here, if I want 0.025 in the right tail of the normal distribution, then I want 0.975 to the left. So we would use our table in reverse. I find 0.975. Find the corresponding z value. So it would be 1.9 for this row, and our second decimal place is a 6. So I get 1.96. Okay, so that's the red circle on the following table. So that's where I get this term. The other terms we're just given, we substitute in. The sample size n was given to be 120. So we work this out. It's easiest to work out this term here, again, this is sometimes called the error term. So when we work out the error term, we get 0.66. So I have my sample mean plus or minus 0.66. When I take 36.1 minus 0.66, you can see we get 35.44. And when we add up here, we get 36.75. So we could say, our 95% confidence interval is given here. And the thinking is that there's a 95% probability that the true mean is within this interval. Okay, again, in part B, we are told, suppose a researcher believed that, before the experiment, the population standard deviation is 4. What's the required sample size to estimate the mean? Want to be within 0.5 with 99% confidence. Okay, so we know that we have a nice straightforward formula for this. N is equal to Z alpha over 2 times sigma over E. Our E was given 0.5. Our standard deviation is 4. And for 99% confidence, we need to think in terms of this Z, 0.005. In other words, with 99% confidence, we're going to have an area of 0.005 in the left tail and an area of 0.005 in the right tail. So if we were looking up this value, think about the right tail, I would have 0.005 in the right tail, which leaves 99.5% in the left tail, or as a decimal, it leaves 0.995 to the left. So using this table here, the value I would look for is this one right here, 0.9951. We could probably use this one as well. But the Z value that we'll use here is 2.58. Okay, so that's how we get our Z term in this solution. This 2.58 comes from the table. So we would work out this fraction, and then we square it. We'll get some number. So here you see we have 426.01, but there's a special rounding rule here because we're trying to guarantee a maximum error. We always round sample sizes up. So even though we're very close to 426, this gets rounded up to 427. So that's our required sample size. Okay, so that concludes example 1. Let's take a look at another example involving foot sizes and shoes. Suppose the foot size of 16 men was measured, resulting in a sample mean of 27.32 centimeters. We'll assume that the distribution of foot sizes is normal with population standard deviation 1.2 centimeters. Test the claim that the population mean of men's foot size is 28.0 centimeters using alpha is equal to 0.01. Okay, so we have a sample mean here, 27.32. We're testing this claim. We see the sample mean comes up just a little bit less, but is that significant? Well, it's hard to say. Okay, so let's go through this hypothesis test. We'll use the 5-step method. So the first thing to observed are, the null and the alternative hypotheses. There was a claim that says that the population mean is 28 centimeters. We'll label that the claim versus the alternative. And here there was no indication as to whether we're interested in the mean being greater than or less than. So we have mu is not equal to 28. Okay, so this is sometimes called a two-sided test. We were given that alpha is equal to 0.01. Since sigma is known, we know that we could run a z-test, and our test statistic is given by this formula. Z is x bar minus the hypothesized mean divided by sigma over the square root of n. So the rejection region, okay, is the solution to the absolute value of z greater than z 0.005. Okay, so in other words, we want to look at the area that has 0.005 to the right tail, and 0.005 to the left. So once again, we saw this just before, our value would be 2.58. So you could see this right over here. Once again, if I have 0.005 to the right, that leaves 0.995 to the left. So that value is 2.58. And the normal distribution is symmetric. So really our critical region would be any value greater than 2.58 and any value less than minus 2.58. So we go ahead and we now substitute in the values to calculate z. So we were given the sample mean, 27.32 minus 28. That's the hypothesized mean. We see this up here. Standard deviation 1.2 over the square root of 16. So when we work this out, we get minus 2.27. Okay, so that's between minus 2.58 and a positive 2.58. So it's not in the critical region, right? We could also express this in terms of absolute values. The absolute value of z is 2.27. It's less than 2.58. So our statistical conclusion is do not reject the null hypothesis. Now in step 5, we want to calculate a p-value. And to calculate a p-value for a two-sided test, we find phi of minus 2.27, and we have to remember to double that. So if we look up minus 2.27 in a normal table, which we'll take a look at over here, okay, minus 2.27, so here's minus 2.2, I would come over here, and minus 2.27 would be in this column. I would get 0.0116. Okay, so that's phi of negative 2.27. We have to double that, so our p-value turns out to be 0.0232. And we compare this to alpha. Alpha is 0.01. We see this is greater, so that confirms our conclusion here. Do not reject the null hypothesis. Remember, when the p-value is greater than alpha, we do not reject. When the p-value is less than alpha, we do reject. There's a phrase that I often use to try to remember that rule. When p is low, the null must go. In this case, P is not low. So some sort of summary sentence here would be, the data supports a claim that the average foot size is 28 centimeters. Okay. But the p-value sort of tells you just how close things are with respect to this conclusion. You might notice here that if the more common alpha equals 0.05, see here it's 0.01, but if it was 0.05, then the conclusion here would be just the reverse. So it's important to take this into consideration. And this is a fairly low p-value, but larger than 0.01. Okay, so next I'd like to just mention a couple of formulas that sometimes come up in problems in Chapter 8. The first group, this is where you're asked to find the probability of a type 2 error for mu. Remember, alpha is the probability of a type 1 error, but if we want to find a beta, okay, the probability of a type 2 error, okay, the first thing you have to do is examine your alternative hypothesis. Okay, so we have, the three possibilities. So this is the situation when you have a two-sided test. And we're going to calculate beta for the problem we just went through, which was a two-sided test. So that's why I put a little arrow here. We're going to use this formula here. Do that in a couple of seconds. But before we do that, I want to show you also formulas for sample size calculations. Again, depends if you'll have a one-sided test or a two-sided test. So the formula for a sample size is given by this formula over here. So here, notice you have two terms here, two z terms. One corresponds to alpha, and the other corresponds to beta. Okay, so we'll take a look at an example involving these formulas. So, continuing example 2, okay, recall that, alpha was equal to 0.01. Suppose we want the probability of a type 2 error when the population mean is 27.0. So that's our mu prime. Okay, so we'll come back to part B in a couple of seconds. Let's take a look at the solution to A. So using the formula that was in the table we just looked at, we're going to calculate beta of 27. Right, so this 27 will be our mu prime. Okay, alpha was 0.01, but here we want to look at z alpha over 2. So z alpha of 0.005. Okay, you may recall that that's 2.58. We've looked at that a couple times already. Okay, and again, the normal distribution is symmetric, so you could see over here minus z of 0.005, that's minus 2.58. Over here in the numerator, I have the hypothesized mean, which is 28. Mu prime, 27. Again, that comes from here. The population standard deviation was given, and the sample size 16 was given. So we simply need to now work this out, work out the fraction. So this fraction simplifies to 5.91. So we need to take phi of 5.91. We'll do that in a couple of seconds. And then over here, I have a similar calculation, but now we have negative 2.58. this term is the same as before. So when we work this out, we get minus phi of 0.75. Okay, so at this point, we need to think about our normal distribution table, but you might notice that in here, this z value is greater than 3.5, right? The table doesn't really give you values when z is greater than 3.5, but we can take this to be 1, right? Because the table is giving you the area to the left of a certain z value. Once z goes beyond 3.5, that area is essentially 1. So we take 1 for this, and then phi of 0.75, we look that up. Let's take a look at that. So phi of 0.75, you can see we have this in the blue circle. So 0.75 right here. So we get 0.7734. That's where this number comes from. We do the subtraction, and we end up with a beta of 0.2266. So that's a fairly high beta. What one would do if you have a beta that high and you want to improve things is simply we need to take a larger sample size. Okay, and in fact, that's what Part B gets at. Part B asks us to find the sample size required to ensure that a type 2 error probability is equal to 0.1 when, again, alpha is 0.01. Okay, so we could go back to our formulas, and again, the key here is to examine what the alternative hypothesis is. Here it's a two-sided test, so this is the formula that we need. Alpha is 0.01, so I want this z 0.005 term, which we've seen a few times, 2.58. But now I have beta is 0.1, so I want the z 0.1 term. So let's think about that. 0.1, well, if we have an area of 0.1 in the right tail, then we would have an area of 0.90 to the left. So I have to use this table and get as close as we can to 0.90, okay? And if we start looking at these values, we start getting close right around here. Here's 0.9015, but you see this is really closer, 0.8997. So we would use this row, 1.2, and then the second decimal is 8. So I would use 1.28. Okay, so that's where this term comes from, the z beta, 1.28. Sigma, the standard deviation we know, 28. Again, that's the hypothesized mean, and 27 is the mu prime that we were given. So we would work out this fraction, then square it. We get 21.46. And once again, we round up because we're trying to guarantee a certain error. So this rounds to 22. So before we had a sample size of 16, we really find that that is not large enough with the high beta. So here, a sample size of 22 would do a better job of keeping beta lower. Okay, so that's the end of the first part here, inferences for mu when sigma is known. Now we're going to look at inferences when sigma is unknown. We'll ask similar types of questions. Let me first note that if sigma is unknown, and your sample size is greater than or equal to 30, then we could just use S in place of sigma in the formulas and the methods that we just looked at. So if the sample size is large, we could still proceed the way we were doing before. So it's when the sample size is small and sigma is unknown that we have to change things up a little bit. Okay, so we still need to know that the underlying distribution is a normal distribution. But one of the things that changes is when we look up our critical values. Now we have to look those up in a t-distribution. So I have a formula for confidence intervals that you see over here. And it's quite similar to what we had before. I still have x bar, and I have plus or minus. Now I have this term t from a t-distribution, and then we multiply by the sample standard deviation over the square root of n. So this is similar to what we had. Here we're just using a t-distribution. We still have the alpha over 2, but now t-distributions have a new wrinkle, something called degrees of freedom. As the degrees of freedom sort of get smaller and smaller, these curves flatten out. Right? The t-distribution is a symmetric bell-shaped distribution similar to a normal, but generally they get flatter and flatter the smaller n is. Okay, we'll look at a t-distribution table in a few minutes. When testing hypotheses, I have a formula very close to what we had before. Same numerator, x bar minus the hypothesized mean. Now here we're just using an S instead of sigma over the square root of n. The critical values come from the t-distribution with degrees of freedom given by n minus 1. Okay, here's an example. Suppose we have a study of 9 bowlers and their average score was 186. The standard deviation of the sample is 6. Okay, key word here. Standard deviation of the sample. The scores are normally distributed. Construct a 95% confidence interval for the mean scores of all bowlers. Show all work involved. Okay, so here's our formula for the confidence interval. Degrees of freedom is 8. So that would be 9 minus 1 is 8. Okay. A 95% confidence interval implies alpha is 0.05. So alpha over 2 is 0.025. When we substitute in our x bars, 186 comes from here. S is given as 6. Sample size is 9. Okay, we just have to look up this value over here. So this is my t alpha over 2 value, okay, for 95% confidence. So let's check this out. You see the next slide. So these values up here sort of would represent the right tail area. And I have 0.025 is my alpha over 2. So I want to look in the 0.025 column. My degrees of freedom is 8. So follow this red arrow, and you can see where we get 2.306. So that's where we have this value coming from right here. So now we just have to work out the algebra. Again, it's best to simplify the error term first. So this reduces to 4.612. So I take 186 minus the error term. We get 181.388. And then 186 plus the error term. So our 95% confidence intervals, 181.388 to 190.612. So the thinking here should be that there's a 95% probability that the true mean is somewhere in this interval. Okay, and with our last example for this video, we'll take a look at a hypothesis test for the mean when sigma is unknown and our sample size is small. So suppose we go to a BMI application, body mass index. Adults with BMI over 25 are considered overweight. Trainer at a health club measured the BMI of people that registered for his program in a certain week. The population is normal, and let's say the numbers are given over here. Okay. So notice when you're given a set of numbers, one of the first things you need to do is find a sample mean, and in this case, a sample standard deviation. It's pretty straightforward with a calculator. You can just put them in a spreadsheet or R. Here in part A, we're asked to construct a 95% confidence interval for the mean BMI, and in part B, determine if newly registered people are overweight on average. Conduct an appropriate test using alpha equals 0.05. Okay, so first the confidence interval. So we make the observation that the sample size is 8, which is considered small. We calculate x bar, calculate s, and we note that the degrees of freedom, 8 minus 1 is 7. So here's our formula for our confidence interval. Notice we're using the t distribution. So I get my x bar. This is coming from the table, 2.542. That's our sample standard deviation over the square root of 8. So let's go take a look at the table. I need to look in the row where the degrees of freedom is 7. Alpha is 0.05, so alpha over 2 is 0.025. So we go over here. Now we're looking at the blue arrow, which is just sort of one line up. Degrees of freedom is 7.025 in the right tail. So I would get 2.365. Okay, so that's where this number comes from. When we simplify the error term, we get 2.126, and then we add and subtract that to get our confidence interval. Okay, for part B, we want to run a hypothesis test to see if newly registered people are overweight on average. So remember, this is a test involving mu, an average. So we want to conduct the appropriate test. So we set up our hypotheses. So we want to know if the average is greater than 25, right? Because then they would be sort of overweight based on the BMI definition. So we could say this is the claim. The alternative is mu is less than or equal to 25. We're given alpha 0.05. So since our sample size is small and the population standard deviation is not known, we run a t-test. So here's our test statistic. Okay, we need to find the rejection region. So now we have a one-sided test. Right? So with a one-sided test, we think in terms of the alpha, the area corresponding to alpha will all be in the right tail. So I need to think in terms of alpha is 0.05, degrees of freedom is 7. Let's go down here. So 0.05, degrees of freedom is 7. You could see that we would get this value right here, 1.895. Okay, so that will be our critical value. So we have this over here. So what this implies is when we calculate the value for t, if t is greater than this value, then we will reject the null, and if t is less, then we will fail to reject. So now we go ahead and run the calculations. So we have our sample mean that we get from the data, 25.425, minus the hypothesized mean, 25 is coming over here. Sample standard deviation that was calculated from the data over the square root of 8. So this works out to be 0.473. It is less than this critical value or the value defining the rejection region. So our statistical conclusion, to not reject the null hypothesis. Okay, so to find the p-value in this case, we need to find the probability t is greater than 0.473. So for this value here, the only way to come up with this value is using some technology. Sometimes we could come up with bounds for p-values and the t. If we look at this and we saw that our value was maybe between 2.365 and 2.998, we could use these as bounds. You'll see that in the book. But for this one here, we could see that our value for, if we go back here, was 0.473. So we don't see anything remotely close to 0.473. So that's why you would have to use technology for calculating this p-value. Okay, so that concludes the video. Good luck with learning all about hypothesis tests in Chapter 8.